Okay, good afternoon. Today I am going to talk about one part of my PhD work, which I am developing with my advisors, Mayra Gonzalez and Deborah Dulci, and my collaborations group. This work is focused in active galactic nucleus, otherwise known as AGN. This figure shows a recently scheme of AGNs, and we can see the different components of these sources. These AGN components have already been introduced in a previous talks. Therefore, I am going to omit this part. I only would like to mention that this work is focused in the torus component in the case of source classified as safer 1 and safer 2. Specifically, this work is focused in the infrared and X-ray wavelengths. I am going to start talking about the X-ray. If we observe the X-ray spectrum, we can identify three main components. The primary emission associated with the emission reprocessed by a corona of the hot electron plasma close to the accretion disk. It scatters the energy in the X-ray band due to inverse Compton. This component is modeled using an energy cutoff power law that depends on photon index and cutoff energy. On the other hand, some part of this primary emission is reprocessed by a dusty torus or a broadline region, and is the origin of the other most relevant component known as a reflection component that consists in two features. A Compton hum that peaks at 30 kiloelectron volts. This component depends on both the geometry and the density of the reprocessing material. And the second feature is the iron Chi alpha emission line, whose origin is the reflection of the X-ray photons. In general, this line is narrow and is associated with a torus. By the reflection component, we need to use a transfer radiative curves that simulates the geometry of the reprocessed material. On the other hand, the continuum emission at infrared wavelengths is dominated by those hated by the AGN. Normally, to model the infrared, we need to use a stellar, interstellar, and those torus components. Classically, to model those torus components, we also radiative transfer models that assumes different geometrical distributions and composition of the dose. In the following slide, I'm going to talk more about this. As I mentioned before, the reflection component at X-ray and the continuum emission and infrared are modeled with a radiative transfer models. Particularly in this work, we explore two distributions of gas and dust. In this figure, we can see a cartoon of the geometry of these models with the respective parameters. In top panel, we can see the X-ray models. Meanwhile, in the bottom panel, we can see the infrared models. The smooth models propose a torus where the gas and dust distributions respectively are uniform and are distributed around a supermassive black hole. Meanwhile, the clumpy models consider a formalist where AGN is surrounded by a toroidal distribution of gas and dusty clouds. Through these models, we can obtain several parameters as inclination and half of penning angle between others. There are very few words that try to restrict the torus parameters through these X-ray models, because only NuSTAR data give us enough spectral range to do this. The infrared model have been used in more cases than X-ray to try to restrict these parameters. Here there is a list of words where the mid-infrared models are used to infer the properties of the torus. Note that in both wavelengths, it's difficult to constrain the parameters only using these models and these spectra. Therefore, the goals of these works are to explore if the X-ray reflection component and the mid-infrared continuum of the AGN are linked to the same structure, is to say, the so-called AGN torus, and to investigate if the combination of the X-ray and infrared spectra and different torus models could help us to restrict the torus physical parameters. In our previous work, we fitted simultaneously the NuSTAR spectra using the smooth models and the Spitzer spectrum with each of the three mid-infrared models for the case of AC 5063. In this work, we found the dosy torus parameters for the AC5063 are better constrained when we simultaneously feed the mid-infrared and X-ray spectra with the smooth models. All dosy torus parameters are found when the inclination and half opening angle are linked to between both models. This link between parameters suggests that the same structure producing the reflection component is emitting through the dose hating mid-infrared. Now, we choose a sample following the next two criteria. The first criterion is that a Spitzer spectrum should be dominated by AGN emission. In this figure, we can see the Spitzer spectrum together with a BLT and Gemini photometric observations. This comparison between photometric data and spectrum allows us to make sure that the spectrum corresponds to a central region less than 100 parsecs. In the future, we can apply this technique using a photometric data, and this could help us increase our sample. Our second criterion is that the reflection component should dominate. In this figure, we can see a NuSTAR spectra, and we can see the different two components, the reflection component and the intrinsic component, and the total fit. Our final sample contains 23 objects. The final sample consisted in 47 AGNs, 24 safer 1 and 23 safer 2. And then our next step is applying the simultaneous fitting technique to this sample of AGNs. But before, what about the individual fittings? We fitted these 47 sources with four models, and we discard the source with a bad statistic. Therefore, we were able to compare the resulting model for 35 AGNs with a good spectral fit about wavelengths. We use the Akaike statistical criteria to select the best model of each wavelength. This table summarizes these results to each source and to each wavelength. We found that 71% of sources are consistent with a combination of smooth X-ray and clumpy and near-infrared. We propose two scenarios to explain this result. The first scenario is that gas has a smooth distribution occupying the intercloud medium, or the gas is located at the inner dust-free region or above the dust-free region and the intercloud medium. About the X-ray and near-infrared parameters, in summary, we found that many of the parameters are not well restricted. Here you can see two tables when we summarize the number of sources where we are capable to constrain each parameter. And particularly, thank you. Particularly in the case of X-ray, we are capable to constrain more parameters to several sources, and we compare the parameters of the smooth and clumpy models. Here you can see a column density of the smooth versus the column density of the clumpy, and you can see the safer one, the clumpy model. In the smooth models, the safer one has a more column densities than clumpy. Our conclusions are we find that 71% of sources with a good spectral fit. The models that better reproduce the X-ray and near-infrared spectra are smooth and clumpy respectively. And we discuss the possible scenario to explain this result. Our results reinforce the link between near-infrared and X-ray obscuring structures. Sorry. In a future work, we apply our simultaneously fit technique to this sample. This could help us to constrain most of the parameters of the dusty gas torus of the source. And then we will study if the toroidal properties change with the kind of the AGN activity. For example, the luminosity, the volumetric luminosity, the accretion rate, or the black hole mass. And this is all. Thank you.
There's what, Donaji, there's one question on Slack for you. And the question is, what kind of X-ray data did you use? Did you use soft X-ray data, hard X-ray data, or both of them?
I use X-ray data and infrared data. I use both. In the case of
the second question.
Yes. Yes.
Go ahead, please answer.
Yes, in the case of the X-ray data, I use the NuSTAR data. And in the case of infrared, I use the Spitzer spectrum, Spitzer data.
Okay. The second question is there a useful observational characteristic of the smooth versus clumpy X-ray model, like we have for the infrared?
Yes, yes.
Yes, there is.
Yes, there is. I don't understand it.
Okay.
Repeat, please.
Is there a useful observational characteristic of the smooth versus clumpy model?
Yes. Okay.
In the X-ray. So how can you distinguish between smooth and clumpy in the X-rays?
Okay. Because how do you distinguish? Because in the if you you can is true. This comparison is through a statistical model, a statistical criterion, and you can with a Kaike criterion you can distinguish between that what model is better fit to the data. But the parameters are very similar, except for the case of because in the smooth model you can are the same, yeah, are the same. The parameters are the same in the X-ray models for the clumpy and the smooth.